que te vaya.
Thank you very much, and sorry for the delay. Well, the opportunity of giving a talk here at GTI is an honor, and so I would like to thank the organizers for the invitation. I'm going to speak about some work made through different collaborations with Hamid Afshar, Stéphane de Tournai, Daniel Grumiller, Wout Mervis, Alfredo Perez, and David Tempo. And it has to do with different possible choices of boundary conditions that one can do for general relativity on AdS3. So in summary, I'm going to focus mostly on a family of boundary conditions that is labeled by an integer. And it is such that in a particular case, one recovers the Brown-Henneaux boundary conditions. In another particular case, the boundary gravitons evolve according to left and right movers that are described by the KdV equation. And also in a kind of extremal case, in the sense that I'm going to explain later, one can also recover a new set of boundary conditions in which a kind of soft-Harry black holes, where soft-Harry is defined in the sense of Hawking, Strominger, and Perry, can be accommodated. Okay, so as a motivation, let me recall some few remarks about the ADM formalism. So in the ADM formalism, the lapse and the shift are the functions that describe how a space-like surface deforms as it evolves in time. And so, in the case of a theory that's invariant under diffeomorphisms, like it is the case of general relativity, the lapse and the shifts turn out to be Lagrange multipliers associated to the Hamiltonian constraints. And so, the common practice when one deals with the asymptotic structure of space-time, is there a glass over here? Ah, you got it. Thank you. So thanks. So the common practice to choose the Lagrange multipliers at infinity is to pick up them to be constant. And of course, this is reasonable because it means that the time and length scales at infinity are fixed, so that observables like the energy are measured with respect to fixed time and length scales. Of course, this is useful and reasonable, but it is not mandatory. So we would like to explore to what extent one can relax this assumption of fixing the Lagrange multipliers to be constant at infinity, and this amounts to allow them to depend on the dynamical fields. So for simplicity, I'm going to focus in the case of three-dimensional gravity with negative cosmological constants. And the outline of the talk is the following. Just for simplicity, I'm going to describe the problem in terms of a Chern-Simons action and gate fields, because it's simpler, nothing deep with that. And so I will focus in the asymptotic structure, identifying the asymptotic symmetries and constructing the conserved charges. And so I will try to be as generic as possible, and then I will focus in some particular examples. So one particular example will be the one of Brown-Henneaux, then the other one that so that the gravitons, the boundary gravitons are described by left and right KdV movers, and then I will show how the family can be extended in such a way that is described by an integer k, and for a generic choice of k, the left and right movers are follow the field equations of the kth representative of the KdV hierarchy. And so in particular, with this choice of boundary conditions, one can see that a sort of anisotropic scaling is inherited, that it turns out to be relevant for what follows. Okay, so then, once the boundary conditions are specified, I'm going to explain how the BTC black hole behaves once within this set of boundary conditions, paying attention on the global charges and thermodynamics, and also how the entropy in particular depends on the energy and the temperature, and this goes by hand with the anisotropic scaling. Well, so paying attention in the anisotropic scaling is relevant because pretty much like in the case of a conformal invariance, one is able to, relying on the anisotropic conformal scaling, one is able to generalize the Cardy formula accordingly, and with the generalization of the Cardy formula, one is able to recover the entropy of the BTC black hole for this choice of boundary conditions. Well, so I will end up making a summary of the results in terms of the space-time metric, And then I will focus in a case where, in some extreme sense that I'm going to explain, soft Hairy black holes can also be accommodated within the set of boundary conditions. Okay, so nowadays the description of general relativity in 3D as a Chern-Simons theory is well known, and also Andrea was talking about that yesterday, so I will be brief. So, up to a boundary term, the action of general relativity with negative lambda can be written as a difference of two Chern-Simons actions. Each of them is evaluated in two independent SL2R gauge fields, where Li stands for the generators of SL2R, and K, the level, K is related to the AdS radius L and the Newton constant in this way. So here the bracket stands for the trace in the fundamental representation of SL2R, and the link in between the gauge fields and the geometry is done through this equation, where E stands for the drive-in and omega the spin connection. And so the space-time metric can be reconstructed from the gauge fields in this way. Okay, so before specifying the boundary conditions, let's explore the generic fall-off of the solutions. So this was explored long ago by Cuszar-Henneaux and Van Driel, and also slightly generalized soon ago in these references. So the trick to deal with the generic fall-off is that the gauge fields can be suitably, there is a suitable choice, a gauge choice, in such a way that all the radial dependence can be gauged away. And so the remaining analysis can be done in terms of these auxiliary connections, which depends only on T and phi. This helps a lot. And so the asymptotic behavior of the space-like part of the gauge field, the auxiliary gauge field, looks like this, where this describes deviation with respect to a massless BTC black hole, and the deviations go along highest weight generator. So that's why we call it the highest weight gauge. Okay, so this space-like part of the connection, and the time-like part of the connection is given by this Lie algebra value function that looks like in this expression. So in summary, if we plug this into the field equations, one can see that the asymptotic behavior is described by two functions. L turns out to be the dynamical field. Mu is a Lagrange multiplier because it has no dot. And so the field equation just says that the time derivative of the dynamical field is the Schwarzen derivative of the Lagrange multiplier. This is for the generic fall-off. So far, we haven't, we know the generic fall-off, but we haven't yet specified which are the boundary conditions. The boundary conditions become specified once we choose precisely the form of the Lagrange multiplier. So, for instance, in the case of Brown-Henneaux, they choose the Lagrange multiplier to be constant that can be suitably scaled to 1. And so now we want to explore which possibilities we have in the choice of the Lagrange multipliers. So, we have a lot of freedom, but the freedom is restricted by the action principle. So let's see what the action principle tells about. And so, the Chern-Simons action is already written in terms of forms, so it is weakly, it's already written in Hamiltonian form if we split time and space-like coordinates. And so the action looks like this, where B stands for suitable boundary terms that have to be added so that the action attains an extremum everywhere, not only in the bulk, also at the boundary. Okay, so if we vary the action, we find that the field strength vanishes in the bulk, and the variation of boundary term is given by this expression. This in general, taking into account the generic fall-off described before. So for this generic fall-off, the variation of boundary term is given by this guy. But this is just the variation. We need to integrate the variation in order to specify the boundary term. And if so, we have some integrability conditions here. And since we have assumed that the gauge fields A plus and A minus are independent, the integrability conditions are easily solved by requiring mu, the Lagrange multiplier, to be the variation of certain functional. Okay, so if we choose the Lagrange multipliers to be given by the variation of h, where by simplicity h can be assumed to be a local functional of the dynamical fields and the derivatives, we have solved the problem. So, in summary, the generic choice of boundary conditions that is allowed by the action principle is such that the Lagrange multipliers come from the variation of a functionals h. By simplicity, h can be assumed to be local functions of L and the derivatives. This assumption can be relaxed at the end. And if so, this is the suitable boundary term that allows to have a well-defined action principle. So in summary, different choices of h specify different choices of boundary conditions. Okay, so let's try to see how far we can reach for a generic choice of boundary conditions. So we already know the fall-off of the fields. And so if we want to identify the asymptotic symmetries, we have to look for the gauge transformations that preserve the asymptotic form of the fields. And so, for instance, in the case of a phi, the gauge transformation that preserve the form of a phi are described by Lie algebra valued parameters that are not completely arbitrary, but they precisely acquire the same form of the time component of the gauge field. But now, instead of depending on the Lagrange multiplier, they depend on two arbitrary functions on t and phi. And so the asymptotic form of the gauge field is mapped into itself, provided the variation of the dynamical field is the Schwarzian derivative of the parameter. So this is what we obtain if we want to preserve the asymptotic form of a phi. So now if we proceed in the same way, but for the time-like component of the gauge field, we find that the field equations have to be fulfilled at infinity, and also the variation of the Lagrange multiplier have to fulfill this equation. But nonetheless, the Lagrange multipliers are not independent, because in general are functionals of L and L prime and derivatives. And because of that, we have a consistency condition, and that applies for the parameters. So if you want to preserve the form, the asymptotic form of AT, the parameters have to fulfill this equation. Well, so in summary, the asymptotic symmetries are such that the variation of the dynamical fields is given by the Schwarzian derivative of the parameters, and the parameters are restricted according to this equation. Okay, so since we have identified the asymptotic symmetries, now we can quickly, following the canonical approach, write the variation of the canonical generators, and it is rarely found to be given by this expression. And so by consistency, if the variation of the charges are requested to be required to be conserved in time, one recovers precisely the same condition on the parameters that we obtained from the analysis of the asymptotic behavior. So this equation is very important for the problem. And this is because of the following, because if we want, for a generic choice of boundary conditions, H depends on the dynamical fields. And because of that, a generic solution of this equation will be such that the parameters epsilon will also depend on the dynamical fields. And that's why it's not so easy to integrate this equation. I mean, we know precisely the variation of the global charges, but it's not so easy to integrate the variation unless we know the solution of this equation. And so for a generic choice of boundary conditions, this is a hard task. But nonetheless, if we still continue with the generic choice of boundary conditions, if the choice doesn't explicitly depend on time or the angle, one can readily find the form of the angular momentum, and also the variation of the energy by virtue of this condition integrates according to this formula. So, in summary, the role of H plus and H minus not only specifies the boundary conditions, but also specifies the spectrum of the theory, because it determines precisely how the energy is computed. Okay, so for a generic choice of boundary conditions, we know the angular momentum, the energy, but in practice we do not know how to integrate this equation. So in order to continue, it is better to try to explore some precise sets of boundary conditions so that we would be able to integrate this equation. Okay, so in order to do that, there there is no precise way of fixing the boundary conditions because different boundary conditions describe different physical problems. But so let me spell out some sensible criteria that are not mandatory but are welcome in order to solve the problem. So certainly if we want to solve this solution, it is good to have as many asymptotic symmetries as possible. And also in order to know the full phase space of the theory, if we have an infinite number of asymptotic symmetries, this certainly will help in order to solve the problem. So both criteria are certainly met in the case where H is chosen as in the case of integrable systems. So this is what I'm going to do next, but first let me try to explain the simplest possible boundary condition that we can do within this framework. So imagine that we pick up the Lagrange multiplier to be constant, that can be suitably scaled to 1. And if so, mu comes from the variation of H, and H has to be given by L. Okay? So if we choose mu to be given by this, mu equals 1, the generic form of the field equation reduced to the fact that the dynamical fields are just described by chiral movers. And also the condition that the parameters have to fulfill reduces to the same, the parameters have to be chiral too. And so, since in this particular simple case, the parameters do not depend on the dynamical fields, the variation of the charges can be readily integrated to this expression. Okay, so for this choice, we know precisely the value of the charges, and also we have identified asymptotic symmetries, and so the algebra can be either directly computed from the Poisson bracket or by this identity by the variation of the charge, taking into account that the variation of L is the Schwarzian derivative of epsilon. And if we do that, one quickly recovers that the asymptotic symmetries are spanned by 2 copies of the Virasoro algebra with the Brown-Henneaux central extension. So let's say this is the kind of quick crash summary of the Brown-Henneaux boundary conditions, the simplest choice within this framework. So now let's try to pick up another choice for mu. Remember that mu comes from the variation of a functional that depends on L and the derivative. So a simple choice would be picking up as mu equals L, just for simplicity. Okay, so if we do that, mu comes from the variation of H, where H is half L squared. And if we plug the form of mu inside the generic form of the field equations precisely reduce to the ones of KdV. And so, for this choice of boundary conditions, the boundary gravitons are also chiral, but now they evolve according to the KdV equation, left and right movers. Okay, so despite it is a simple choice, we have found something non-trivial that is fulfilled at the boundary. Well, and also the condition that the parameters have to fulfill reduces to this equation. So we want to continue. In summary, what we want to solve, we want to find the generic solution of this equation that is linear, but nonetheless, L fulfills a non-linear equation. But nonetheless, KdV is an integrable system. And because of that, fortunately, we know the generic solution of this equation, provided epsilon is assumed to be a local function of L and the derivatives. Okay, so the solution of this equation can be expressed as an expansion, but if we compare with the Brown-Henneaux boundary conditions, the solution of the equation can be written as expansion in Fourier modes. For these boundary conditions, the solution of this equation is also an expansion, but instead of being given in terms of Fourier modes, it is given in terms of the so-called Gelfand Dickey polynomials. And the Gelfand Dickey polynomials are defined through this recursion relation, where there is nothing, the normalization is not important. And something that is known in the literature is that the solution of the recursion relation is such that the Gelfand Dickey polynomials come from the variation of certain functionals. Okay, so this works in this way. If we plug the first trivial Gelfand Dickey polynomial, we put 1 here, the recursion relationship tells us that the next one is L, and so on. And so we're ready to integrate the charges because the variation of the global charges has this genetic expression. Now we know the solution of epsilon, that is a linear combination of the Gelfand-Dickey polynomials, and the Gelfand-Dickey polynomial comes from the variation of certain functionals, so we plug epsilon here, taking into account that R comes from the variation of H, Q is integrated readily in this way. Okay? And so it is simple to verify that the algebra associated to the asymptotic symmetries turns out to be abelian and devoid of central extensions, which naturally goes by hand with the fact that the integrable systems, like in the case of KdV, are such that the conserved charges are in involution. So this is the next example, and let me make some remarks about it. Well, we have an infinite number of conserved charges, and the first 4 of them are given by this expression. So you can see that as the label of the charge increases, the complexity of the charge also does, but in a controlled way. And so we have an infinite number of conserved charges, and the special one that describes the evolution in time is the energy. And so one can check that the energy of a generic configuration with these boundary conditions is given by the sum of the energies of left and right KdV movers. That goes like L squared. Say it again, please. It is not a deformation because, let's say, in the case of Brown-Henneaux, we have mu equals 1, and now we have mu equals L. It's not 1 plus L. Do you see what I mean? It's not the deformation of the Brown-Henneaux boundary conditions. It's a different set. Well, it should, but I'm not entirely sure which would be the suitable one. Well, I'm going to speak about later. Well, somehow what you can say is that the metric at the boundary depends explicitly on the dynamical fields, but I'm going to that at the end. So please be patient. Okay, so now we have the ingredients to make a kind of compulsory choice, because we have somehow rediscovered the Gelfand-Dickey polynomials. And we know that the Gelfand-Dickey polynomials automatically come from the variation of certain functionals. And this is precisely what we need in order to define a boundary condition. So imagine that we choose the Lagrange multipliers to be precisely given by certain kth Gelfand-Dickey polynomial. If so, we already know that the Gelfand-Dickey polynomial comes from the variation of the kth Hamiltonian of the KdV hierarchy. And then the Einstein field equations with these boundary conditions reduce to the kth representative of the KdV hierarchy. So we have left and right movers that evolve according to the kth equation of the KdV hierarchy. That, let's say, I mean, if we pick up k equals to 47, this can be very complicated. And so it will be the condition that the parameters have to fulfill. So nonetheless, and quite remarkably, the Gelfand-Dickey polynomials have very nice properties that are such that, in spite of the fact that the complication can be very complicated, and also this other one, the solution of the equation that the parameters have to fulfill is precisely the same as the one for KdV. This is quite remarkable. So, I mean, let's say pick up k equals to 45, we have a very complicated equation, but the solution of this equation is precisely given by an arbitrary linear combination of the Gelfand-Dickey polynomials. And so, because of that, we can again integrate the values of the charges. So we have precisely the same asymptotic symmetries, like for k equals 1. But the difference is that now the energy is given by the kth Hamiltonian of the KdV hierarchy. So, in summary, we have an infinite number of symmetries. They are abelian. And for a fixed value of k, the energy is given by the Hamiltonian of the KdV hierarchy. Okay, so something that also deserves to be highlighted is that with these boundary conditions for a fixed value of k, the boundary gravitons actually possess an anisotropic scaling. This is known in the literature of KdV. An anisotropic scaling in the sense that it will scale phi with the constant lambda. So the time coordinate has to be rescaled with the same function but to certain power, that the power is given by 2k plus 1. And if we also rescale the dynamical fields in this way, the field equations are invariant. And so, in summary, with this set of boundary conditions, the field equations reduce to the kth representative of the KdV hierarchy, which naturally processes this anisotropic scaling symmetry. And then actually this turns out to be inherited by the full AdS spacetime, but I'm going to speak about the metric later. Okay, so we have the set of boundary conditions that is labeled by the integer k. And so a natural question is to explore how the BTC black hole behaves once it is embedded within the new set of boundary conditions. And so it is simple to verify that the BTC black hole corresponds to the case of L plus and L minus equals to a constant. And so the field equations are trivially fulfilled because L dot vanishes, and at the right hand side we also have at least one derivative along the phi. So for L plus and L minus constant, we always solve the field equations. And in the case of AdS, is recovered when L plus and L minus is equal to minus 1. Okay, so we know the energy. We know that for a generic configuration, the energy is the sum of the left and right movers that fulfill the KdV equation. And so for the BTC black hole, left and right energies expressed in terms of the dynamical exponent C is given by this power of L. And in the case of AdS, the energy actually depends on K. So, I mean, if we pick up our preferred choice of K, then C is given to 2K plus 1, and the energy of AdS depends on the choice of boundary conditions. Okay, so now let's see what happens to the entropy. The entropy is given by a quarter of the area, expressed in terms of the dynamical fields, gives this familiar expression. But the entropy is a thermodynamical quantity, and so it has to be expressed in terms of the extensive variables that in this case correspond to the left and right energies. And so once the entropy is expressed in terms of the left and right KdV, the energy of the left and right KdV movers, the entropy depends on these funny powers of the energy. And also, one can do the same in terms of the energy and the temperature. And so the entropy in terms of the left and right temperatures reads like in this formula. And so this is funny because from what is known from a non-relativistic holography, the dependence for the entropy in terms of the energy or in terms of the temperature acquires the right power in terms of the anisotropic scaling. So this is nice, but actually we can do something better. We can recover the quarter of the area with all the factors if we focus in a precise generalization of the Cardy formula that one can do in that case. Each of them possess the same scaling. I mean, left and right movers scale. No, this is the anisotropic scaling, and so we are assuming. I mean, not assuming. We know that both left and right movers possess precisely the same scaling properties. Well, in T and phi. No. This is the case of the Brown-Henneaux. It would be left and right movers that are chiral, but here the left and right movers evolve according to the KdV equation. So in the KdV equation, it's funny because you have solitons, kind of solitons, and solitons move just in one way, and the waves move the other way. Okay? They're chiral in the sense that they depend on, we have two copies, and each copy evolve according to the KdV equation. For the KdV equation, solitons move in one way, and the waves move in the opposite one. And so we have the same, but let's say the opposite for each copy. That's right. They evolve according to the KdV equation. No, yes. So let's say the KdV equation possesses soliton solutions that the velocity depends on the amplitude, and asymptotically in time, it has been shown that you can have some initial profile, and asymptotically, this turns out to be described by the sum of solitons moving in one way and waves moving in the opposite. That's it.
Can I also ask for in this slide, is that AdS, not on the other side? Just do one AdS, but AdS doesn't, the deduction of that, but AdS is not invalid. It's not that symmetric. Doesn't have the isommetry.
No. When I say AdS, I mean the full, the global AdS. What I'm doing is making a different foliation of AdS, because the Lagrange multipliers turn out to be, this I will explain at the end, but the Lagrange multipliers actually determine the lapse and the shift. So I have global AdS foliated in a funny way, but it's global AdS. It is not, yes, but no. What one can prove is that this symmetry is a symmetry of the family of solutions we're dealing with, because we have to rescale also the dynamical fields. So technically, if you apply this as anisotropic invariance, you start from one solution L and you end up with another solution. Okay? So that's it. No. The symmetries act like the Schwarzenberg derivative of the parameters. Give me a second. Here. So we have a family of metrics that I'm explicitly showing at the end. And the family is such that when you act with an isometry that's spanned by epsilon, the variation of the fields is described by the Schwarzenberg derivative of epsilon. This is the action of an asymptotic symmetry. That's larger than an isometry. Yes. Say it again. It depends in the way you boost. What do you mean by boost? If you apply an asymptotic symmetry to boost them, there is no way to fail. Well, in the case of the Brown-Henneaux, k equals 0 does, but generically, no. No, they don't. Yeah. So for these boundary conditions, the suitably notion of boosting would be boosting along the asymptotic symmetries that are identified. The asymptotic symmetries are spanned by, now they are spanned by these guys. Well, I would say one could define a boost. No, I wouldn't say the isometries of the vacuum. I would say the asymptotic symmetries. You can pick up your preferred solution, you act on it with an asymptotic symmetry, and by definition, you span a new solution. So now, according to this game, the asymptotic symmetries are spanned by these guys. Not for a generic choice of boundary conditions. That's right. No, the charges are defined for the asymptotic symmetries. That there's a larger group than the isometry. No, the isometries hold just for particular solutions. So, it depends. Isometries are just particularly symmetry that you find for one particular solution. But it's not what we're looking for. What we need to look for is the set of asymptotic symmetries. And to that, one associate charges.
Perhaps let's let Ricardo get to his point, otherwise we will run out of time.
Okay.
So maybe you can carry on and we can come back to this at the end.
Yeah, okay, so I was describing how the BTC black hole looks like once embedded within the new set of boundary conditions, and so also the energy of AdS depends on the precise choice of on C, and so the entropy generically acquired a non-trivial dependence on the energy and also on the temperature. And so I was about to explain how this dependence, the entropy can be reproduced from a generalization of the Cardy formula that has to do with the anisotropic scaling. So let's forget about gravity for a while, and let's consider just some theory with anisotropic scaling in 2 dimensions. So in the case of finite temperature, the theory is defined on the torus, where the angular coordinate runs from 0 to 2 pi, and Euclidean time runs from 0 to beta. And so pretty much like in the case of S-duality in conformal field theory, we swap the role of the angular and the angular coordinate of Euclidean time. Then we can use the anisotropic scaling in order to fit the period of phi. And if we do that, we can establish that different tori, whose temperatures are related in this way, are equivalent. And so one can see that for C equals 1, one recovers the expected result. And so once we establish how S-duality looks in the case of an anisotropic scaling, it is reasonable to assume that the partition function is invariant under the duality. So now, if we have left and right independent left and right movers that possess the same scaling, so it is natural to describe the torus in terms of a complex beta. And if so, the anisotropic S-duality relation we look for acquires this form, which certainly reduces to the standard one for C equals 1. And so, okay, so in general, this is the anisotropic form of S-duality, and if we assume that the partition function is invariant under this S-duality, we are ready to find the anisotropic version of the Cardy formula. So how do we do that? If we assume that the spectrum, so question, please. Yeah. Look, we didn't study the whole set, but at least if you restrict just to the S duality, this one closes. I mean, we didn't do the whole SL2C analysis, but we just focus in the S modular property. Yes, no, it is. No, it is. Yes, because when you swap the role, C goes to 1 over C, and so it closes. Yes. C less than 1? The well, KdV has C equals to 2k plus 1. In the case of KdV, but here I'm dealing with just with an arbitrary value of C. No idea. Perhaps there is some expert on. Say the question again. Where? I think it has to be true, because I mean, in the theory, if you assume that the theory is invariant under the scaling symmetry, the action has to be, and if so, I mean, swapping the roles in the Euclidean theory, swapping the role of phi and the Euclidean time is just a coordinate transformation. So the theory is assumed to possess the scaling parameter. This is just an identity. Say it again. Okay. So I have to rush. Okay, so in summary, if we assume that the spectrum possesses a gap and the energy of the ground state is given by minus delta naught, at low temperatures the partition function is dominated by the energy of the ground state, and by virtue of the anisotropic modular S modular invariance, one knows how the partition function looks like at the high temperature regime. And from this, one can readily evaluate the asymptotic growth of the number of states, and it's given by this expression. Okay, so here one can see that in the case of C equals 1, one recovers the Cardy formula where the role of the central charge is played in, by the energies, by the ground state energy. Okay, so let's put well, and since I have to rush, from the Cardy formula one can also obtain a generalization of the Stefan-Boltzmann law. I mean, the energy depends on the temperature in this way, and also the entropy in terms of the temperature is given by the expression. Okay, so let's put everything together. Let's consider the choice of boundary conditions for which the left and right movers follow the KdV, the kth KdV equations. So if so, the entropy given by a quarter of the area is given by, once expressed in terms of left and right energies, is given by this expression. Okay, so besides, we know from an isotropic S modular invariance that the generalization of Cardy formula is given by this other expression. So it's quite remarkable is that if we identify the energy of the black hole with the energy of the theory with an isotropic scaling in 2 dimensions, and if we also identify the ground state, the energy of the ground state of the 2D theory with the energy of AdS, if we plug this here, we precisely reproduce the entropy of the BTC black hole with the KdV boundary conditions. Okay, so time is running, so let me try to go fast and concerning your question. So one can do everything from scratch or reproducing, reconstructing the metric from the Chern-Simons approach. And if so, the asymptotic form of the metric acquires this form, where this calligraphic n and m phi relate to the Lagrange multipliers mu mass and mu plus and mu minus in this way. And so that the lapse and the shift are given by these guys. And so the functions that appear here relate to the L plus and L minus and the calligraphic n in this way. So the asymptotic form of the metric is not so illuminating, but nonetheless from here one can see that the boundary metric manifestly depends on the choice of mu, which in turn depends on the dynamical fields and the derivatives. So that's it. And well, one can proceed all the way with the asymptotic form of the metric, and one recovers the same results like in the case of the Chern-Simons theory. And also the asymptotic symmetries are given by this cumbersome expression, but nonetheless, using the standard Hamiltonian approach to construct the charges, we precisely derive the same results like in the Chern-Simons formalism. Okay, so, and just to end, let me try to make a link with another, this is another, sorry, no, because this was not the last version of my talk. Sorry. Well, so there is another choice of boundary conditions that is seemingly disconnected from the ones that I've been dealing with. But what is curious is that if we express that boundary conditions in the highest weight gauge, one can say that for that boundary conditions, the choice of Lagrange multipliers turns out to be non-local, because the Lagrange multiplier would be given by this expression where what is fixed is C, and the dynamical field can be expressed in this way. So this has to do with the fact that Shaheen was talking about that the Virasoro currents can be written in terms of different currents that fulfill the an affine U1 algebra. But well, what is interesting about this set of boundary conditions is that they accommodate sort of soft-Hairy black holes, which are stationary but not necessarily spherically symmetric. So let's say the horizon is a kind of wiggly function where these ripples turn out to be described by the U1 charges. And so it's interesting in the sense of soft-Hairy and in the sense of the proposal by Hawking, Perrin-Ström. Well, so in summary, what does this set of boundary conditions has to do with the KdV ones? So remarkably, they are related in this following sense. So we want to construct the full hierarchy of boundary conditions. We can start with the Brown-Henneaux ones, plug in mu equals 1 here, the recursion relationship gives us the next one that is KdV, and so on. Okay, so now imagine that we try to force this formula to work back. So I mean, the question is whether there is a kind of precursor from which the Brown-Henneaux boundary conditions appear. So if so, we should plug the Brown-Henneaux boundary conditions here. So mu equals 1 here gives 0. So what we look for is in the kernel of the Schwarzian derivative. Okay? And quite remarkably, this what specifies the soft-Hairy kind of boundary conditions precisely solves the kernel of the Schwarzian derivative. So in that sense, one can see that this soft-Hairy kind of boundary conditions turn out to be the precursor of the whole KdV hierarchy. And so I have to stop. Thank you very much.
Thank you. Just one question. Yes, please.
I know an extreme with which kind of boundary conditions?
So in your KdV, you were talking about generic BTZ, but for extremal, I think some
L
things
plus is equal to L minus. That's it. I mean, generically there is no problem to deal with them with KdV, but with this set of boundary conditions there is a problem. But L plus is equal to plus or minus. L minus defines the configuration, and there is no problem with that.
And may I ask a short question?
Up to him, huh?
Okay. So I was just thinking that your charges are independent of radial coordinate, the r.
Is there the charges?
Yeah, because
they are.
the expressions are independent. And in principle, you can define them on the horizon.
Yes, you can define that at any fixed
And
value.
how do they act, how these transformations act on the horizon? Let's remember that horizon is a null surface, and with the generic KdV, probably you are not going to remain on the horizon. So
I know how they act precisely at any value of the radial coordinates, I mean, in between the horizon and at infinity, but how they act, I'm not entirely sure. There might be some subtlety in the Hamiltonian formulas, and so I wouldn't dare to just say that is the same action that I'm writing here. So on the horizon, I do not know. I mean, naively, since in the Chern-Simons approach, the charges do not depend on R, I would say that the action is precisely the same I have shown, but I would be careful.
Thank you, and let's thank Ricardo.